Hi, everyone. So welcome to week 4 for 165 CL. We're going to start on lab module 2 and begin planning and working our way through that. In terms of our goals for today, we're going to briefly review the important material science concepts that are behind the nucleation and growth of new phases. We're going to choose the material system that's going to let us dig into that. And then we're going to design our experiment and come up with a matrix of key variables to be explored. So the first thing to do is recognize, in our lab module 1, we learned about the beginnings of phase diagrams, how we can look at things like solubility limits. It's important to recognize what are the limitations of these diagrams. So they can tell us what phases will be there for a given temperature and composition, for example, including what the composition of the different phases are and what the phase fraction is. But it's not going to tell us how to get there, okay? So for example, if we're at this point here on this phase diagram, it will tell us that we, in this case, it's aluminum copper, because that's what we're going to spend a lot of time talking about today. We'll have a single phase solid solution. And we also know that if we decrease the temperature and go to the 2-phase region, we're going to have 2 phases. We're going to have a solid solution plus some, in this case, an intermetallic, copper aluminum 2. What the phase diagram doesn't tell us, though, is how do we get between these 2 states? And then also it doesn't tell us how that second phase is organized within our microstructure. So we're going to start to poke around with that today. Now, the way the sort of kinetic processes that we go through to go from 1 to 2 phases has a few important steps. One of the first is this early nucleation step. Now, when we were working in lab module 1, we were doing a liquid and a solid transition. And in fact, when you have a solid nucleating out from a liquid, it's relatively easy. So you can have local fluctuations that create clusters. In this case, there's atoms moving around. A few of them find a local region that they like, and they start to form a crystal. That nucleus can then just grow and become that second solid phase. So there's very little barrier to this happening in a liquid, and it could be pretty straightforward. Solids have additional restrictions, and the issue there is that the solid phase has to somehow deal with the fact that it might not match up with the other solid phase that it's right next to. Okay, so for example, if I put a face-centered cubic solid phase in a liquid, there's not really a big deal. But if I want to put a face-centered cubic phase attached to a body-centered cubic phase, I have an issue. There's now a pretty high energy interface that's formed. So instead, what happens is rather than have this abrupt change in the material, it tends to nucleate the second phase through a relatively subtle process that's shown here on the bottom, schematically on the left, and then some transmission electron microscopy images on the right. Taking that aluminum copper example, so the aluminum phase, which is FCC, starts to have clusters that are copper rich. Now, these don't form a whole new phase at the beginning. Instead, they just form a region where locally there's more copper than on average. Okay, and these actually are so common that they have a special name. They're called Guinier-Preston zones or just GP zones. And if I look, and I can see these in the electron microscope. Now, the thing I want to point out here is all of these atoms are projections of atomic rows, atomic columns. And if you look, you find that all the columns match up, which tells us that the crystal structure hasn't changed. The fact that these are brighter has to do with the fact that there's a different element located along that GP zone there. The second step is once these GP zones start to grow, eventually they can get big enough, they can form a full 3D precipitate. The chemical composition of that new phase is going to agree with the final product. But usually the next step is that the particle maintains the crystal structure of the matrix. So in this case, our matrix is gray and it's starting to form this gray and blue ordered compound. And chemically, it's got the right percentages, but it doesn't have the crystal structure it likes. Instead, it's just trying to match what the matrix is doing. So what happens is you have a large energy penalty for having a strained phase and sometimes even not having the right crystal structure that your material wants. but you only have a small energy penalty because you have a coherent interface, okay? So the blue is a generally good thing, the red here is a bad thing. As these start to grow, eventually those particles will get bigger, the volumetric energy component win out, and you're going to form a precipitate that has its native structure and lattice constant, but now has to form an incoherent or non-matching interface with the matrix. So in this case, that blue and gray phase has formed this different crystal structure. It's happy by itself, so it's relatively low energy, but there's an energy penalty from having this new interface. Okay, and on the bottom is just showing an example of incoherent precipitates that have nucleated out into a matrix inside grains or along grain boundaries. So the overall picture of this evolution is that we go from a single phase solid solution to these GP zones that are almost two-dimensional or platelet type phases, to 3D precipitates that are coherent with the interface, with the matrix. And then eventually we'll get to incoherent precipitates that don't match the matrix and sort of exist totally on their own. Now, the other thing to mention is that even after we step through this process, that second phase can continue to coarsen and grow, right? This is just showing an example of this on the bottom. This is a polycrystalline microstructure. So these different colored regions are all different grains. And inside of them, there are these precipitates. So pick one of those grains, you're going to find those precipitates in there. And if you heat treat this for longer and longer times, you'll find that you'll eventually have growth of these precipitates so that they get bigger and bigger and bigger, okay? The phase diagram doesn't say any of this stuff, right? It just says I have one phase or two and what their composition is and how much of it, okay? And these two pictures, you could have the same amount of second phase, it's just organized in space differently. Now, what we're gonna do, so I was showing these pictures and these sort of little schematics of what's happening inside of your material. We're gonna study this in a certain alloy system, but we're not going to go in and look at these different phases. So these little GP zones, for example, are really tiny. These are a few nanometers across. And to really go in and see that, you would have to go and use some really beautiful transmission electron microscopes. It would take you months to get one image and get one data point, okay? Instead, what we're gonna do is we're gonna use the fact that all these different stages of what's happening with these second phases come out can interact with dislocations in our material and affect the strength, okay? So all of these things we talked about will strengthen our material. On the left here this is showing an atomistic simulation of a dislocation moving through and interacting with a GP zone. You can also think about something similar happening with full-blown sort of precipitates that have fully nucleated and grown, either where the dislocation has to cut through the precipitates or it has to bow around. Now, in all of these cases, what's important is that these defects increase the strength of my material. So generally the strength increment that you get is going to be proportional to a bunch of things divided by one, or divided by the spacing between the precipitates. So to get a really strong material, I'd want to have lots of precipitates in there, but I'd want them to be relatively small and finely spaced. Right? And on the bottom here is just showing a sort of real world example from a TEM image where these precipitates are cut and sheared by those dislocations moving through. So we're going to use mechanical strength as a metric that we can track and understand this type of process. So in terms of choosing a system, there's sort of many things you could pick. I chose this aluminum copper system for a few reasons. First, it's well known and widely available. So there's a good, very reliable phase diagram. This material is used in industry and all over the world, so it's well studied. But the other reason is if we're using mechanical strength as an analog, I'm going to want there to be a large difference in the strength between the two phases that I'm having coexist inside the material. So on this left side, the aluminum by itself is a pretty soft phase. And if I go right into this two-phase region, I see that I'm going to get aluminum, FCC aluminum, plus some intermetallic, some compound, that copper aluminum too. And what that means is that I'm going to have a relative mixture of a relatively soft and a relatively hard phase. So this should be good for seeing these types of effects that we're looking for. Now I'm going to zoom in on that aluminum-rich side of this region. So we're going to be thinking about aluminum with just a little bit of copper in it, and how we can look at this two-phase nucleation and growth. So if we look at this region that I highlighted on the last slide, it looks pretty simple. We don't have to worry about all the stuff going on in the copper-rich region. We can think about if we move from this single-phase aluminum-rich system and just lower the temperature, we can end up getting this two-phase region, right? I'm going to choose a commercially available alloy. This is an aluminum alloy called 2024. These numbers have to do with what alloying elements are mixed in there. And it's so easily available that I could just go on to McMaster Car and purchase a bar of this material for relatively cheap. Okay, so I went and purchased a bar that looks like this. It's 1 inch in the widths, and it's 3 feet in the length. Okay, now this 2024 aluminum alloy is mainly aluminum. The primary dopant that's in there is copper, so it usually has about 4 to 5% copper. It usually has a little over 1% magnesium, and then it also has just a tiny bit of manganese, chrome, silicon, iron, titanium, and zinc. And I said less than 1%, but in many cases these are much smaller. It's 0.1% or something like that. So the reason I picked this is it's, again, easily available, but it's primarily aluminum copper. And the other thing is that this amount of 4 to 5% copper keeps us in below that solubility limit of copper. So if we heat it to the right temperature, we can get a single phase FCC solid solution. So the experimental methods we're going to use, we're going to have to use some polishing methods to make our samples so that we can do all these experiments. We will be heat treating them inside this furnace so that we can control the thermal history of the materials. And then we're going to measure those mechanical properties with this hardness testing. I mentioned it briefly before. We're going to come in and poke on the surface and then look at the indents or residual indent that's left on that surface. And we'll go through some examples in coming weeks to talk about how to run this type of experiment, how to analyze your data and things like that. Okay, last but not least, we're going to use some optical microscopy. For example, this type of equipment lets me go measure those indents one by one, whereas I can go and just measure them as a batch inside of the optical microscope, get slightly better images of that. For our remote version, it's also nice because there's a video camera on the microscope. There isn't on the hardness tester. All right, so in terms of our heat treatments, we're going to have to do a two-step type of process. So I just bought this material from McMaster Car. I don't know what they did with it. They could have heated it to different temperatures, held it there. They could have done cold rolling where they did plastic deformation to increase the strength of the material. I have no idea. So what I'm going to have to do is take my material and the first thing I'm going to do is I'm going to do what's called solutionize my material. I'm going to heat it up and let it sit at that intermediate temperature that is in that single phase region. And I'm going to let it sit there for a while and form that single phase solid solution. Okay. If I go back to my phase diagram, this is going to be at about 550 degrees Celsius. So after I let it sit there for a little while, what I'm going to do is I'm going to quench down my material, and then I will heat it to some intermediate temperature, let it sit there for a given amount of time, quench it back down at different times, and measure my hardness. So in terms of what my expected data would look like, I can think about measuring the hardness as a function of these heat treatment times. I picked two main heat treatments. I picked 200 degrees C and 150 degrees C. These would give us largely the same fraction of that second phase. So they're not so different that they're going to give us different phase fractions. The real difference is the thermal energy that I'm giving to allow that second phase to come out, okay? So this higher temperature should allow that second phase to precipitate out and grow much faster than this lower temperature, right? And for that, I'm going to do 0. So right after I solutionize, 1, 2, 3, 4, and 5 hours, and then 1 day, okay? The other thing I'm going to do is also study what happens at 20 degrees C, okay? So we talked about heating up and allowing these second phases to come out. And usually we think about increasing the temperature to something high enough that that can happen. Well, aluminum has an interesting type of behavior that its melting point is relatively low. It's only in the 600s degrees C. So what that means is we need to remember that Celsius is not an absolute temperature, okay? We really want to convert that to Kelvin and think about sort of what temperatures we're working with there. So if it's 600 or a little bit over 600 degrees C, that means it's going to be about 900 Kelvin. And if we think about that room temperature, even though it says 20 degrees C, that's almost 300 Kelvin, okay? So even room temperature is about a third of my melting point. So I'm going to do what's sometimes called natural aging. I'm going to solutionize a sample, quench it down, and then measure just as it's sitting on the lab bench at room temperature, nothing crazy happening to it. How does its mechanical behavior change over time? So I'm going to repeat these experiments, do it at these different 1, 2, 3, 4, 5, and 24 hours. And then I'm also going to throw another time point in for this one and come back after leaving it in the lab for a week and testing what its properties are. So one thing I want to point out is that generally we're just going to have one value in this 0 time spot, because this is going to be the sample that I measure right after that solutionizing treatment, right after we quenched it. Okay, in theory, all the other steps are coming right after. Now I'm also going to go in and obtain the hardness of the as received material. I'll give that to you at the very end, and we can maybe compare and contrast that with what we're measuring during this type of experiment. Okay, so I posted a video. Again, you can grab it from the link in the slides, or you can go to our homepage where I'll have the link directly. And this is talking about the sample preparation necessary to get our experiment ready. So we have these big bars of material. We need to cut them into smaller pieces, and we also need to polish them so that they are a uniform shape, but then also have a nice polished surface for us to look at. I will step you through those processes. On the bottom, I'm just showing you an example. These are 2 of the pieces that we're going to use. This isn't the final step. The final step, they've been polished, so they have a mirror surface. You don't see any of these scratches, but if you look closely, you can see that there's some scratches going horizontally on this sample on the left, and some scratches going vertically on this sample on the right. And this is just connected to how a sandpaper is scratching along those surfaces. Okay, so please go watch this video. It will give you an idea of how we've prepared our specimens and got ready to run this experiment. And that brings us to the end of today. So read through that, try to understand why we're studying this material, what kind of things we're looking for. And then next week, we will jump into those heat treatments and then do hardness testing after all of these different things. All right, enjoy the rest of your day, and I'll see you soon.